Good morning, folks. This is it's 10:30, and your lecture is going to start. Can you please tell me if you can hear me? Can you hear me? Excellent. Thank you. Thank you. All right. So today is going to be your second presentation for shells. We're going to have another one. We're going to have another one for you folks on probably Monday afternoon, or if you are in section 54, it's going to be Tuesday morning. That's going to be also on shells. So altogether, we had 3 shell presentations, shell lessons, and of course, I have posted 4 different versions of homeworks which deal with shells. So that was posted on YouTube last night, and you can access it. And this is going to be the homework that you're going to turn in next week. Okay. The moral of the story is that we had enough time spent on these shells, and temporarily after next week, the first lecture of next week, these shells are going to go away, but they're going to resurface in about 10 days. Because at some point, we're going to make models that have not only solids in them, but shells in them and beams. Okay, we call these hybrid models. So they're going to pop up. Okay, but in about 10 days. Now, the problem that I did for you probably on Tuesday, it was a folded sheet metal which had uniform thickness on all pieces. The bottom of those edges were the bottom of the edges of the folded sheet metal was clamped, and the surface was pressurized. Now, I did it different from how it's done in the book. However, at the end, I came back and I said, if I was to follow the book's approach, what would happen? Okay. In fact, I'm pretty sure I also did it for you the way the book was done. It's done in the book, but towards the end, at the end of the presentation. What we like to do today is look at the situation where this folded sheet metal, for example, does not have the same thicknesses on all pieces involved. The specific problem that I'm going to be doing for you is from chapter 11. And as you can see, it's talking about mismatch in shell thickness. Now, the problem that we're going to be looking at is this bracket. This bracket, the top of it, is subjected to some kind of a load. There's a circle up here, so some kind of a load. And this side face, side circle is clamped. Okay? Now, the thicknesses of these 2 pieces are different. Okay? I think the thickness are different, so I don't know. I take this thing as 0.1 and this one as 0.05. Now, I will do this problem 2 different ways. Okay, 2 different ways, and the first one is not the way it's done in the book. Okay, so I will create the surface directly and without using the concept of surface extraction, okay, or without using a solid object. Okay. After I do that and I show you the nitty-gritties of that, we're going to come back and see how it's done in the book, and we'll get there later. We'll get there later. Okay. Now, you have to solve this problem. If this problem was given to you on the test, we would clearly say, use the most appropriate element, and you should realize that this is a shell element. Even if I had drawn this thing as a 3-dimensional object with that, the grayish thing, remember the grayish thing that is solid object, even if I had drawn it, you have to solve it with shell element. Okay. Now, the other thing is that we're going to ask you to use all planes of symmetry. So when you look at this problem, this circle is clamped. This circle on the top is subjected to a total load of, I don't know, 100 pounds here. 100 pounds, when you think about it, stare at it for a while, do problems. I mean, these are things, these are skills that you're not born with it, but you with experience, doing problems, discussing it, etc., you learn it. There is a plane of symmetry here, right this way and down. So basically, you need to model half of this, and you have to if you're going to be if this problem is given to you for assessment purposes. Okay. Now in the book, not only it's done differently, with using surface extraction, symmetry is also not used. Okay, but today when I do it, the book's approach, I will again use symmetry. Okay, there is a final slide here. Maybe this final slide I'll come back and talk to you after I do the problem. Okay, where is this? Okay, so let's start with a part file. Immediately save it. So file, save management, save as, desktop, new folder. So this is, I'll call it section, today is May 28, section 2, lecture. How about that? Section 2, lecture. You are in section 2. You're either in lab 53 or 54. Okay. And I'm going to give it a name. The name is your student ID, 1, 2, 3, 4, 5, 6, 7, 8, 9, dash. Your last name, Euler, dash. I'll call it folded bracket, direct surface generation, as opposed to surface extraction the way it's done in the book. Okay, so we say, move this thing out of the way here, say save, come on, okay, and we're going to make it. So on this plane, I will sketch that inverted L. So it looks like that. Put some dimensions on it in a second, like this. Let me see now. What were these dimensions? It was 10 and 5. Okay, very good. So this dimension is 10. This dimension is 5. 5. We're going to exit. And we're going to extrude that to create the surface directly without using a solid object. So we're going to do mirror extent and 2.5 in each direction, total of 5. And the reason I do mirror extent because I want to be able to cut it with that middle surface easily without doing too much work. That's all. It doesn't have to be, if you don't have a middle plane, you have to go create it, etc., etc. Okay, so on that top face, I will sketch that circle because I want to split that. Is that right? Yep. Okay. Normal view. Draw the circle of diameter 1. Its diameter is 1. And it's 2.5 inches away from the top face, top edge. So from here to there, 2.5. Okay. Exit. Well, I can split it now. Make a hole here. I can wait and do the other one and do it at that point. Okay, fine. Let's do it now. Here's the split, the saw. Read carefully. It says element to cut is here. Cutting element is there. And there we are. Notice that I did not join the surface. Okay. I said when in doubt, join it. I don't have to join it here because I drew the L and extruded. So when you think about it, there's a single line here, single line. But if you do it the book way, that you make a box this size and extract the top face and extract the side face, on this edge, there is two lines, one from the bottom surface, one from the top surface. If you join it, essentially it becomes one line, okay? Here I don't have to, because when I extruded it, just give me one line. But as I said, if you extract, there are different lines on the two sides, and when you join it, essentially it becomes a single seam, okay? All right, and this will save us in a sense, because when you mesh this piece right now, you get the same node numbers on the left side and on the right side of the seam. But if these are not joined, you get different node numbers here, different node numbers there. They may not even match at the location, and then you have to do some extra work. We'll talk about it later. Okay, let's do this guy. On this face, I will sketch the circle right there. Let's give it a dimension, and diameter is 1. Exit. Why don't I split it now? Just be careful here. Don't panic. Notice that I didn't mean it, but that circle is selected. It's orange. You can see that. So if I say split, it thinks that I want to split that guy, and then it goes nuts. You know, things like that. It thinks that I want to split this sketch, which is not the case. So cancel that. Click on the screen so that this is lost, and then split surface with that guy, okay? And we say okay. There we are. See this? These holes. Now, I'm going to split. Read it carefully. Element to cut is that entire extrude, okay? Or if you join them, that entire join. And the elements to cut, cutting element is that middle plane. So you take either this side or that side. It really doesn't matter. There we are. Anything that you don't need, you don't want, just hide it. These sketches, you can't delete them. You have to hide it. Okay, hide, etc. Good. Now, let us apply material on this. So where is this guy? Apply material right there. We're going to make it out of steel. How about that? Metal, steel. On the top piece, we say okay. We're good. And this is it. So because I already did all the preliminary work for naming this thing, all I have to do is to click on the floppy, and it's going to save it, and I'm done here. So now we're going to go to generative structure analysis. So CATIA doesn't see any solid object. There was none here. So we're going to say, okay, you do the meshing. You're on your own. So let me change the rendering here. Okay. The only shell mesh that we know is this. Notice that in here, there is the solid mesh, there is the beam mesh, and there is a shell mesh. This is the only type of shell mesh that we know. When you go to advanced meshing 2, there is a variety of different. This is the worst one. Let's think about that way. Okay. So notice that when I select anything, the top or the bottom, it takes the whole thing, even without a joint, because of the concept, the fact that this is an extrusion, okay? But if you do it the book way, and if you don't join, the top is going to be meshed separately, the bottom is going to be meshed separately, and because of that seam, there is multiple node numbers here, and there's a problem, etc., etc., okay? But not here, 0.3. I'll make this thing yeah, okay, this is point, okay, 0.2, see how it looks. And I'm making it linear. That's too big. So let's do it again. Double click on it. Actually, I made a mistake. I changed the sag. I meant to change this. We'll talk about the sag later on at some point. Oh, look at this. Look at this. No. It's linear. It's going to run fast, but that's a disaster. Oh, no. I changed the sag again. Not this. I want that guy. 0.4. Okay, very good. Not the sags. The size. You can look at the mesh, right click, mesh visualization, you see okay. There we are, you can look at it from close by. And if you put the cursor, for example, on this element, notice that it runs on the seam. It runs between nodes 43 and 44. If I go below, it's the same nodes, 43 and 44. Okay, let me rotate this so that you're convinced. 43, 44, 43, 44. Okay, this is element number. Okay, very good. Deactivate. Deactivate. Excellent. Now, 2D property, the thickness of the shell. The problem is that thicknesses, here is 0.1, here is 0.05. Okay? The previous problem that I did for you, previous meaning on the, no, I think it was on Tuesday, is this was all same thickness. Here, I have 2. So, just like what you did with the beam, first put 0.1 on the whole thing, and then do a local shell property, change that to 0.05. So here is the 2D property. On that, which is going to take the whole thing, let's put a 0.1 on it. That's the top, everything. And then I'm going to make this thing 0.05, only this. So you put the cursor on the property, and this is exactly what you did for beams. You went to properties, you put the cursor there, right click, it says, in your case, in the beam, it says local 1D property. Here is local 2D property. You click on it, and then you go and select the one that you want to change its thickness. This one, right there, right there. And you make that 0.05 instead, 0.05. And you say, OK. Notice that here is 0.05. Overall is 0.1. Obviously, this 0.05 is going to overwrite 0.1. 0.1 is going to be here, but not down there. Now, let's hide the stuff that we don't want. Hide, hide. Very good. Now, we know that this edge is clamped. When I say edge, that means the circular edge. This is clamped. We know that there is a force of 100 pounds on that. And then you lose, I don't know, 3, 4 marks. Because that was 100 pounds on the whole thing. This is half of it. It's going to be minus 50. Okay, 50, not 100. This said 100 on the entire top, top circle. Good. And these are in the plane of symmetry, YZ. Okay? So we're going to say user defined, just to make sure we don't make a mistake. We uncheck all of these, start with a clean slate. Over here, YZ symmetry. YZ symmetry. Which ones? This one, and that one, and that edge, and this edge. Because they're in YZ, they don't move in X. Rotations opposite. Okay. Very good. And we save the analysis. File, save management, analysis, save as, right folder. This is you, right? May 28, section 2, etc. And that name, I gave it a fancy name. 1, 2, 3, 4, 5, 6, 7, 8, 9. Last name Euler. And that stuff that I have there folded. Bracket. Bracket. Dash. Direct. I don't think you can do a cut and paste. You can try it, but I'm pretty sure you can. Dash. Surface generation. Not the book way. Okay, very good. And save. And okay. Excellent. I hope I didn't forget anything. Let's run it and see what happens. So far, so good. Excellent. Just running doesn't mean it's right, by the way, So look at the deflection. This is the first line of attack. Does it deflect the way we expect it? And remember, you clamp this and you put a load here, and this is nice and symmetric. Yeah, okay, that's what I expect. Not only that, if you look at the front view, that these edges better not go sideways. And not this one. Let's look at the side view, like that. You see? This edge, because of the constraint that you put it, doesn't go to the left, doesn't go to the right. That's a good sign. This actually is bending. You can see that. Let me turn it around. Let me turn it around. Oh, no, I want the other side then. Okay, like that. Okay, very good. See, it is bending, but it doesn't go to the side. It shouldn't, if there's symmetry involved here. Close. 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 If it doesn't close, just click on something else. Oh, no, click on something else. Click on, I don't know, deflection. Okay, that'll close. Sometimes it gets stuck there. Okay, so deflection. All right. Okay, we put a load here. Let me put it in the isometric view so that you can see it better. Right there. You clamp this, you put a load there, and you got the deflection. And here's the stress, by the way. Okay, so this is this one use stress. You can get that. And let me put the deflection back. And you run to your supervisor. Oh, come on. Okay, if it doesn't open up from here, do it from there. Double click. Average ISO, there. And you run to the supervisor and say, hey, I did it. I did it. This is the result of deflection. And if you want, I can show you the stress. But anyway, so the supervisor will look at you and say, wow, this guy can generate very good looking colors. And he knows his stuff. He knows what he's doing. He knows how to do it. But he has no engineering judgment. Why would that be? Would you like to tell me something? It looked good, looks good. Let me see. Deflection, a foot. You're right. You're right. You're right. Looks good. It deflects most where it's supposed to. Look at the stresses. This is 500,000 psi. The yield strength of steel is 30,000. This is 20 times past the yield stress. Okay, good. So let me see. The supervisor said, oh, come on, go fix this thing. So what would your solution be? Before I go there, before I ask you to somebody tell me, one of the criticism of this course may be either by the students or by my colleagues, I don't know, is that, well, you're doing too much stuff and they're doing a lot, but students are not doing a real problem, or they're not analyzing something in detail. That criticism is totally valid. However, I leave it to you guys to start questioning these answers. I leave it to you guys, so once you learn the procedure, to apply these things to your capstone, make meaningful results, not just good-looking colors. Okay? All right. So, yes, I take that. Now, tell me, if you were to address this issue with your supervisor, what would you do? I mean, you see, there's a foot. Okay, obviously this is nonsense. So what would you suggest to the supervisor? These dimensions, suppose that, well, the size of this thing was fixed, for example, and the load was fixed, etc. How would you go about trying to salvage something out of this? What would that be? What would you say? Use your common sense. Don't worry about engineering.
You could put
Yes.
a bracket on the inside of the flange.
Very good. For example, you're going to say, okay, I'm going to put stiffeners here. You're right, you're right, you're right. Stiffeners. Or you're going to say, oh, I'm going to make this thing thicker, right? Agree? Basically, give it more stiffness. That's what the bracket really does. That the stiffener here, like right there, something like that, will give you stiffness so that it won't deflect as 1 foot. The other option is to make this thing thicker, right? So let's go ahead and make it thicker, no problem. So let's go back to our 0.1. Remember, this was 0.1 inch. This was 0.1 inch, no problem. So we go to our 2D property, double click on 2D property. Instead of 0.1, let me make it 1 inch. Would that do it? That's 25 millimeters. Okay, thick piece of steel. Okay, very good. The other one I left it the same, by the way. I'm going to run it. Okay, let's look at the deflection now. 9.8 inches. Help me. So that didn't work. And why is it that didn't work? I made it thicker. You want me to make it 5 inches? Let's go ahead. Make that thing 5 inches. Where is that? Right there. 5 inches. That's ridiculous, but make it 5 inches. That's ridiculous. This whole thing was 5 inches, right? But why not? Oh, I'll get to it. Let's look at the results and see. Right here. 9 inches. This is almost exactly the same number. I think I changed it. Didn't I change it? Yeah, 5 inches. So what's going on? Actually, notice that top plate makes absolutely no difference. The reason that the deflection is so much is that this vertical one is very, very flimsy compared to that. I made it 1 inch, 5 inches, ridiculous. This is 0.05. So actually, this doesn't experience any stress. If this is very thick, and you put a load here, it's going to move as a rigid body. It doesn't do much bending, but it will take this guy with it. It will take this guy with it. So what may stop this is not taking this thicker, but maybe taking that, making it thicker. As a matter of fact, let's go ahead there. Let's go ahead there. And for 2D property, let's put it back to 0.1 that we had before. Okay. And this local one, instead of being 0.05, let's make it, I don't know, maybe 0.1, maybe 0.15, I don't know, whatever you want, 0.15, and run it. So I made this thing thicker. I left this thing alone. Excellent. Let's look at the deflection now. 2 inches. That's more reasonable. Okay. Or if you go and make this, instead of 0.15 inch, this vertical one, instead of 0.15 inch, 0.2 inches, run it. What was that? Did I say 0.2? 0.2 is about 5 millimeters, okay? I think I made it 0.2, I'm not sure. Deflection? Yeah, 1 inches. The moral of the story is that these all look the same color-wise, but there's more to it than the color. It's very easy to generate good-looking garbage. Okay, so I expect people to look at things that they do they don't make sense, to discuss it with myself, with the GA, you know, etc., to sort it out. Okay, and yeah. Okay. All right. Any questions? Because I want to repeat this problem. Except that I'll do it the book's way. Yes. Who? Okay. Do you have a question?
Yeah, I'm just curious, if we wanted to fillet that 90-degree angle, would we have to go into a 3D, like go out of beam and go into a 3D? Or does CATIA kind of, would
Okay.
it
When
take
you
a
say,
radius?
let me ask you this: when you mean put a fillet there? Is that what you're saying? A fillet, right? Is that what
Yeah,
you're
like,
saying?
yeah, if we
Okay.
change the 90-degree angle to like a
Let's
small
do that.
radius.
Yeah, let's do that. Let's do that. Go to your part. Go to your part. There's your part. This is the part. If you double click on this thing, it's in the background too. But if you double click it, it puts in the part design. Go to the sketch. Go to the sketch that you drew. This was the first sketch that I drew. Cancel. Where's my sketch? There's the sketch that I drew. Put a fillet that you want right there. Right there. Is that good? That's all right. Okay, good. Exit. I could have put a surface fillet too. Either way. Now you back to your analysis. Everything is going to carry over. Let me show you the part. There it is. There we are. You want to see your mesh? It's going to take care of that. You see? And then run it. Yep. Does that answer your question?
Yeah, I think so. I didn't know if it behaves like an actual fillet or if it just behaves as a radius, like a thin radius. Because
Well,
a fillet has more material in it, so I didn't know if CATIA takes that into account.
no, it won't take that in.
Okay.
The way I described it to you, it just makes a radius there,
Yeah,
but it
okay.
doesn't fillet more material. It doesn't do that. No.
Okay.
Now, by the way, if your job was to design that fillet, that corner, your primary responsibility was that area, then you're not going to use shell elements. You're going to concentrate on that area and use solid elements just for that area.
Yeah, okay, that's what I figured, but I
Okay?
wasn't sure if CATIA accounts for it or not.
No, it doesn't. No, it doesn't. Okay? Any other question before we move on and do it the way the book does it? Let's kill this.
Yeah, sir, could you just quickly repeat the significance of joining it or not joining it in this
You
case?
will see that. You will see that. You'll see
Okay,
that. When I do it the book way, you'll see that.
all right, thank you.
Okay. I don't recommend that you do it the book way, but who knows? It could be that the particular, you have to learn these things because they're going to come out in different form, okay? And you'll see that effect. Okay, so we start with the part file. Okay, and immediately save it. File, save management, save as in that same folder, but I'm going to change the name. I'm going to say surface extraction instead of direct surface generation. Folded bracket, surface extraction, which is the book's way. Surface extraction. Okay. Say okay. Say okay. So I'm going to make a box here. And since I'm talking about making a box, I better go to part design, by the way. Box is a solid object. Okay. So on that vertical plane, I will sketch a rectangle that is, or a square that's 5 by 5. Some dimensions here. 5, 5, and 5. Okay, exit, padded by 10 inches. Okay, all right. Now I need some holes on the top because remember when you extract this top face, you want a hole there. So I'm going to make the hole right now. Why don't we make it right now? Okay, so a hole there. I tried to make it coincident with that. I think I did. So this is 1. And the position of it is from here to here, 2.5. 2.5. Okay, exit. Let's make a pocket all the way to the end. Very good. I also want on this side, on this face, so I will draw, fit it. Okay, circle right there. Again, diameter 1 inch. Okay, exit, pocket all the way to the end. Okay, now remember, when it comes to shell, we're going to have to cut this thing. So I have two choices. I can cut the solid object and extract, or I can extract and then cut that piece later on with wireframe and surface. I'll cut it here. Okay. In the book, there is no cut. Okay. So where's this? There's a saw here. There's a saw here, right there. This saw will cut three-dimensional object. You click on it. With what plane? This plane. Which side do you want to keep, this side or the other side? I'll keep the other side so you can see it better. There we are. Okay, let's apply material to this thing. Made out of steel, metal, made out of steel. On that part, we say okay. All right. Now I want to extract these faces. As soon as you say faces, it's a surface. There's nothing you can do with surfaces in the part design workbench. You have to go to generative shape design. And for those of you who don't have this thing, who don't have it customized, you go here, start, shape, I don't know, generative shape, right there. Okay. Look for extract. So there is a toolbar called extract. It looks like something is pointing to that kind of surface right there. You click on it. By the way, I did this thing for you last time for the problem in chapter 10, as it's done in the book. There is one, and do it again for the side, and there's another one. Hide this. Don't delete it. You can't delete it. If you delete it, then these surfaces are going to go with it, but I can hide it. Now, the difference between this thing that I did and the surface that I generated like that, exactly like that for you, is the fact that here at this seam, I have two lines. If you put the cursor close to it, you see it takes an arrow. So there is a line which belongs to the top geometry, that top surface. And if you slightly move it down, there is a line that you're picking and comes from the vertical. These two lines are not the same. When you mesh the top, it's going to have nodes on the top line. When you mesh the side, it's going to have nodes on the bottom line, and they don't match. In the way I did it, because there was no top and bottom line, that you had identical node numbers here from the top or the bottom. If you join it, this problem will go away. Right now, if you don't join, and I'm not going to join it, I'm not going to, if you join this, join these two surfaces, the rest of the problem is exactly like before. But I will not join it to show you how we fix it, because in the book, these are not joined. Okay? Now, the other thing, regardless of whether you join it or not, the problem is that we have a solid object in the background. And CATIA, either way, is going to mesh that for you, and you're going to have to delete it. We talked about this thing last time. Okay? So let's do it. I'm not going to join it to begin with. Okay? To give you a hassle, to show how it's done in the book and what needs to be done and what's going to come to us in about 3 weeks. Not join. So at least I can say, oh, so let's say I did all the preliminary work. So I just click on the floppy. And now we're going to go to generative structure analysis. CATIA sees a solid object sitting in the background, hiding back there. It said, I'm going to mesh you. And it did. This mesh is no good. Get rid of it. Delete it. And don't forget to delete the property of it that was automatically created also. If you don't, when you try to run it, it's going to come back, hey, this is an orphan property. I don't have a mesh that goes with it, so what's this? Anyway, delete it. Yep, pretty much. starting from scratch. Just like you did with beams, you do it with shells. Now, because you did not join these, when you select, you can only select the top or the bottom. You can't do it at the same time. So you select this, it's going to mesh the top one. I'll make this thing a little bit smaller so you can see it better. Okay, linear. Okay. And if I say, show me the mesh, it will only show you the top because I haven't even meshed the bottom. Okay, deactivate this. Now mesh the vertical side. I'll use the same size. Now when you say show me the mesh, it'll show you both. And you cannot do this thing simultaneously. If you join them, it'll do it for you right away. And look close. They don't even match necessarily. Look, this guy from that side and this guy from the top, they don't even match. Even if they match, they will not have the same node number. Okay, so let me keep it the way it is. Show you what's going to happen. Let me keep it the way it is. So deactivate this and proceed just like we did the rest of the problem. First of all, 2D property. No problem. Here, because I did not join, when I select this, you specify the property for that, 0.1. And when you do it again, you select this, he'll do it for that, 0.05. You can do it. If you join them, when you select it, it's going to be the whole thing. And then I showed you what to do, local 2D property. But not here. You don't do that. Let's clamp this. These steps are exactly like before. Apply load here. The good thing is that it remember what I did a few minutes ago, so I don't have to type it in. That can be dangerous too. Okay, there is your -50. And if you select the user defined, it picked the right stuff because we did it correctly last time. So this edge and this edge and this edge and that edge. Say okay. Let's save our analysis. File, save management, analysis, save as. In that folder, except that this is not the direct surface generation, it's the analysis for surface extraction, I think I called it. Folded bracket, surface extraction. Book's way. The only difference between the book and what I'm doing here is that in the book, the symmetry is not used. On the test, you have to use it. Unless you use it otherwise, and I will not say otherwise. Okay, good. Now, let's run it and see how it bombs out, and we can see that that seam is going to cause a problem. There. Okay, let's animate it. Maybe it'll tell us something right there. And you can see that these nodes were not talking to each other. They don't know that they're attached to the same thing. They don't know that they have to move along that line. So this top is basically moving as a rigid body. Is there a question? Okay, I'll move on because I want to fix this. I want to fix. Is there a question?
I have a question.
Yes.
Is it possible to use a constraint on that place, like where the surface is sliding? Is it possible to use a constraint there, or we still
No, you cannot do it. There's a very specific way you have to do it. If you think that there is something called constraint and it's going to fix magically all our problem, there is no such a thing. I'll show you how to fix it in a minute. I'll just show you how to fix it in a minute. And this is why that last slide that I didn't go through, it says the surfaces are extracted. You must use something called general analysis connection to handle the mismatch in thickness, or go to the advanced meshing tool. This issue could have been resolved by going to the advanced meshing tool, because in advanced meshing tool there is a feature which says if two nodes are within 1 millimeter of each other, for example, or 1/10 of a millimeter of it, merge them so that those guys from the bottom and the top, they get merged, and they move together. But I'm not taking you there. I'm going to show you with the analysis connection, okay? So here's the situation. Basically, you're going to say, hey, the nodes on the top and the nodes at the bottom of the seam, they are tied together. Think about it like that. In order to do that, this is a very specific way of having to do it, just like you were thinking, constraint and things like that. Yeah, but there is no such thing in constraint. You have to do it like this. Essentially, I'm trying to do what you're thinking, but it's a different context, okay? So first you create a connection. This is analysis support. First one is general analysis connection. Remember, connection doesn't mean they're connected to each other. It's like when I say, for example, I am related to that guy. That may be in the context of the father and son, brothers, cousins, teacher and a student. So just being related doesn't say how they are related. So right now, we are saying that this top line, see the arrow? See the arrow? This is the top line. Second component, the bottom line. See that? I'm selecting the bottom line now. These are related to each other, but I'm not saying how. Once you create that connection, there is a line here called connection that we just created right there. We just created this. You can name it the way you want so that you remember. Once you do that, the relationship, siblings, teacher and student, I don't know, cousins, is done with this. Face-to-face connection. Don't worry about the first one. Don't worry about the second one. It's contact. You're going to see a lot of these. Don't worry about it. Last one, the third one says fasten. Fastened, and I can select this dot that is the connection that I created or the connection from. And watch this. Watch this when I select this. When I select this little dot, see what happens? It puts a fastener sign there. This fastener doesn't mean they're bolted together or there are fasteners there, there are screws there. That's not what it means. It means that points, whether they come from the bottom, or nodes, whether they come from the bottom or the top, they all follow that original line. They all go together. We had an issue because the guys on the top didn't see the guys at the bottom. They just went over it. Now we're going to say, okay. Save it and run it. And just to show you, it's going to work. It's going to work. I'm going to change the scale so that you can see it better. Remember this scaly, when you plot something, you can change the scale. Deformation. Change the scale to default. Ah, that's the way it's supposed to be, right? This is supposed to bend. It's making this guy bend too. You can see that. Not only it bends, but it also makes this bend because these are talking to each other now. And the same thing with displacement and the same thing with stress. So in the book, I extracted the surfaces. The only thing I didn't do is the surface, cutting it. Didn't do that. But to fix the issue, and I didn't want to join it. If I had joined these two, there would have been any problem. There was no problem. It would have been just like the first problem that I did for you. Okay? Yeah. Last thing that I want to do, let me do the following. Let me deactivate this. Let me deactivate that. And you know what I'm going to do? I'm going to also delete these fasten because I want to show you something. And I'm going to delete the mesh, these elements. So let's see now. Where delete. If you want a fancy mesh, you cannot stay here. This is all you've got, either linear or parabolic. This is all you've got. If you want a fancy mesh, and sometimes it's a must, it's not up to you, because these kind of elements are not going to get good result in certain problems. So you go there to the advanced meshing tool, right there, advanced meshing tool. This is the one that we have always gone to. advanced meshing tools. And there's something called surface mesher right there. Incidentally, let me show you. Cancel that. Notice that you know this. This is the one that we have been using for the last 2 days. This is surface mesher. I clicked on it and I select that. And let me make this thing, I'll keep it as 0.3, no problem. Okay. All right. And mesh it. Look at this. Look at this. This you could not have got with the regular shell element that you've got. And there's a lot of things, fancy things that you can do here that you cannot do with the regular three-noded mesh or the linear and parabolic triangle mesh. Okay, not for me, but when you do these things for living later on, these become critical. Okay, so let me also do this other side for you. I did this surface, and I do the other one. There we are, same size, and mesh it. This is meshing it. It's going to look like that, and it's going to go okay. Let's exit this. Back to our analysis and simulation, generative structure analysis, and the usual way, look at your mesh. There. Are these better elements than the one that we have been using? Yes. Do I expect you to use these? No. Why did I tell you that? Because in the book, there's a few occasions that I take you to the advanced meshing tool to get a fancier mesh. You know, I don't want you to panic. Where did that come from? This guy didn't cover it. Anything that's done here, you do it with this horrible 3-noded or 6-noded element, parabolic or linear. Let me stop this, and then if there's any questions, please feel free to ask me. But I would like to stop this. Stop recording it, please. That's what I want to do. Oops.